So molecular shape and polarity. We've talked about polar bonds versus nonpolar bonds. Talked about electronegativity. If we're looking at just a diatomic molecule, just two atoms with a single bond, the whole molecule is going to be polar if that one bond is polar. And remember, we have the arrow pointing to the more electronegative element with the little plus sign on the side with the less electronegative. So this end of the molecule is going to have a partial positive charge indicated with the lowercase Greek delta. This end will be partially negative. It's just a lopsided electron density. And so here in this picture, we see that the electron density is shifted towards the chlorine. In a polyatomic molecule, when you got more than two atoms, it gets a little more complicated. And you still look at the polar bonds, but then the overall polarity is going to depend on the actual shape of the molecule. And that's why we had to talk about Vesper theory first. If the dipole moments of the individual bonds cancel each other out, then the molecule is nonpolar, even though it has polar bonds. So let's look at carbon dioxide. Carbon dioxide has two polar bonds. Oh, I know what I could do. No, that's not what I want. I'm having trouble with my pointer because it will not let me get any lower than this on the screen, which is so incredibly annoying. So here we've got our carbon dioxide molecule. This molecule is linear. We learned that from Vesper theory because we look at the carbon atom. It's got two groups of electrons, two double bonds. Each double bond is one group. So two groups get away from each other by going to opposite sides. It's a linear molecule. Both of these bonds are polar. Oxygen is more electronegative, and so it pulls the electron density away from the carbon. The oxygens are pulling electron density away in opposite directions. So this is a little bit like playing tug of war, right? So here we've got, I'll do it way up at the top here. So here we've got one person pulling on the rope and another person pulling on the rope. Like my artwork? And here's the middle of the rope. They're having a contest and they're both pulling against each other, right? If they are equally strong, is the little flag in the middle of the rope going to move? No. Only if one is stronger will someone win. If they're equally strong, it's just going to be a stalemate. So what we've got here is two identically polar bonds because they're both between carbon and oxygen. Electronegativity difference is the same. They're going in opposite directions. They cancel each other out. So even though this molecule has polar bonds, the overall molecule is nonpolar. There isn't a positive and negative end on the molecule itself. Does that make sense? This means yes. This means no. Okay, I at least got one nod. We'll go with that. We really should think of dipole moments, these polar bonds, as vector quantities. Do you remember hearing about vectors in math class in high school? I got one nod. I got three people nodding. Awesome. Okay, so regardless of whether you actually remember how to do them, at least you know that you've heard of them. So vectors are quantities that have a direction and a magnitude. So you think of them as arrows. The length of the arrow is the size of it, and the direction it's pointing is the direction, right? So here what we have, this pulling is when these guys are equally strong, the vectors are the same magnitude, but the directions are opposite. So adding those together adds up to 0. And that's technically how we should be thinking about this. So I'm going to talk about vectors, and then I'm going to give you a shortcut at the end, which works most of the time. So just bear with me through the real stuff here. Let's look at water. Water also has two polar bonds. They're between oxygen and hydrogen. So the strength of those dipole moments, the magnitudes of the vectors are the same. But now we know from Vesper theory that water is not a linear molecule. Right? There's two lone pairs on the oxygen, and that makes it a bent molecule. So then we have one of these vectors, one of these dipole moments, pointing at an angle towards the oxygen, and the other one also pointing at a different angle towards the oxygen. When we add those two vectors together, they do not add up to 0. right? Because they are not equally opposing each other. So water does have a dipole moment. And you could think about this in terms of, playing tug of war. So here's the dad, and he's playing tug of war with his twin sons. So there's one little boy. You can see why I didn't go into art. Right? There's one rope. Here's another rope. So dad's pulling. Dad's stronger than the little boys. The little boys are pulling against him, but at an angle, not straight out in opposite directions. So how's this whole group of people going to move? Dad's going to be backing up, right? Dad's backing up, tugging both of those little boys with him. Does that make sense? So water's a polar molecule. If we look at the overall electron distribution, there's more electron density at the oxygen end and less at the hydrogen end. And this has significant impact on the chemical and physical properties of water. So, summary. To determine the polarity, you got to start with the Lewis structure and then look at the molecular geometry because the shape matters. If the molecule has polar bonds, then evaluate how those polar bonds are adding together. Think of them as vectors. Do they add together to zero? Then it's going to be a nonpolar molecule. If there's a net vector from adding those things together, then you have a polar molecule. So let's review vector addition. In one dimension, this is a lot like a number line. So here we have, in example 1, two vectors. They each have the same magnitude, +5, meaning they're going both in the same direction to the right. So we just assign a direction as positive and the opposite as negative. And so when we add these together, we get a vector going to the right that's +10. In example 2, we have vectors going in opposite directions. One is -5 and one is +10. So when we add these together, they do not add up to 0. This is like playing tug of war where this guy is stronger than that guy. And so overall, this is going to move to the right, and the net sum is +5. In example 3, we have two vectors of equal magnitude pointing in opposite directions. So there's -5 in that direction, +5 this direction. Those are going to add up to 0. Everybody okay with that? This is really a number line adding positive and negative numbers. A little more tricky when you get into 2 dimensions. So the way you do this, here we've got, in example 4, we've got vector A and vector B. To add those, you're going to draw a parallelogram. So from the end of A, you're going to draw a parallel line, a line that's parallel with the other vector. From the end of vector B, you're going to draw a line that's parallel with the first vector. The sum of those vectors is from the origin of these two to the opposite corner of the parallelogram. And here we're doing it with another example. Any questions? The good news is you don't actually have to do this. I was supposed to teach you about it. If you have 3 or more vectors, now we're going to get into 3-dimensional space. Just do 2 at a time. So add A and B, and you get R, and then you're going to add that sum to the third one, and you're going to get R prime in this direction. Example 7 is interesting. Here we have 3 vectors. These all lie in a plane, but they're in opposite directions. They're going to the points of an equilateral triangle. So if we add A and B, we get vector R. And then we add vector R to vector C. Those are in opposite directions, equal in magnitude. They cancel out. So these 3 vectors add up to 0. Any questions? Clear as mud, right? Okay, so table from your book kind of summarizing this. When we look at the geometries that molecules can have, according to Vesper theory, we have a limited number of possibilities here. So in a linear geometry, if the dipole moments are equal in strength, this is going to add up to 0, and you're going to get a nonpolar molecule. If you have a trigonal planar or a tetrahedral shape, and those dipole moments are equal, you're also going to have a nonpolar molecule, because those vectors are pointing in equally spaced opposite directions, and so they're going to add up to 0. Where you can get a polar molecule is if you have a bent structure or a trigonal pyramid. We're ignoring the expanded octets here. Because here things are lopsided. These are the two types of structures that you're going to find if you have lone pairs on your central atom. So that brings me to my shortcut. This will work most of the time. And I think that's pretty good, something that works most of the time. So this was one you should remember. So a molecule will be nonpolar if both of these conditions are true. No lone pairs on the central atom, and all of the atoms that are bonded to that central atom are the same, or they have the same electronegativity. Okay? For a lot of students, this is easier than thinking about adding vectors. So let's do an example. Determine if carbon tetrafluoride is polar. We got to start with the Lewis structure. Even my shortcut starts with the Lewis structure. So let's do that. I'm going to do this pretty quick because we've already covered details of how to do Lewis structures. So we have to connect these. So we'll put the fluorines around the carbon. We need to figure out how many valence electrons we have and stick those in. And so we're going to end up with something like this. So thinking about vectors, we have to go through and see, well, this carbon has how many electron groups? 4. 4 groups. What do 4 balloons do? They make a tetrahedron, right? That funky shape. What, the balloons? Over there. So tetrahedral. And then are these bonds polar? Yeah. So how do you know without looking at the table? Good rule of thumb is if those elements are different, it's probably polar. The only one you really need to remember that's nonpolar with different elements is a carbon-hydrogen bond. Carbon-hydrogen bonds are considered nonpolar. So these are polar, and so we've got this tetrahedron. Oh, I always do that. So we could draw a picture of this, and it's going to be symmetrical in shape, right? And so if you think about adding the vectors, those are all going to add up to 0. So this would be a nonpolar molecule. So how do you use the shortcut? Look at the Lewis structure. Are there any lone pairs on the central atom? No. So the first condition is no lone pairs on the central atom. The others don't matter. So no lone pairs, okay, that's true. Are all the atoms bonded to the central atom the same? Yes. Also true. Same atoms. Or same electronegativity. So both of those conditions are true, therefore this is a nonpolar molecule. Any questions? Let's do another example because I think my slides here are a little deficient. So we'll do another example. Let's do ammonia. So NH3. I'm sorry, I got lost on my screen there. There we go. I gotta have some reference or I get completely lost. Okay, so NH3. What do we have to start with? Lewis structure. So we draw the Lewis structure, put nitrogen in the middle, hydrogens around like this, and we're going to end up with a lone pair on the nitrogen. Okay, if you're still a little wobbly on Lewis structures, you need to review the earlier part of the chapters. So let's just apply my shortcuts. Is there a lone pair on the central atom? Yes. So the first condition of no lone pairs is not met. Therefore, this is a polar molecule. Is that easier than adding vectors? Yeah, that's why I'm telling you about it. Adding vectors, though, is why. Okay, so it's important to know that there is a scientific basis for this, based in math and geometry and stuff. But the no lone pairs, all the same atom, works really well. So let's just do one more example. You can write it several different ways. Dichloromethane. So this has 2 chlorines on it and 2 hydrogens. And of course the chlorines are going to have their little octets with the lone pairs. Polar or nonpolar? Polar. There's no lone pairs on the central atom, but we have 2 different kinds of atoms here. The chances are excellent that those electronegativities are different enough that those are polar bonds. So this is a polar molecule. The way I drew it, though, looks all symmetrical and nice, doesn't it? Because that's flat, but the actual molecule is 3-dimensional. It's a tetrahedron, and you can't make that symmetrical as a tetrahedron. So that's a polar molecule. Any questions?
So the rule is for polar, not non.
The 2 qualifications have to be met. If both of them are met, it's nonpolar. No lone pairs on the central atom, and all the atoms bonded to the central atom are the same or have the same electronegativity. If either is violated, not true, then it's polar.
Can you see an example where it's not the same element, but it's the same electronegativity?
Yes. Do you know, Ms. Henry? Is it carbon and sulfur that are the same? Yeah.
The yellow periodic tables do have electronegativity.
That's true. I've got one of those here.
There's a role of energy on the other side.
Yeah, I've got one right here. Okay. That's an excellent question. Okay, so let's pick a couple of things here. Okay, so hydrogen and phosphorus have the same electronegativity. This is a hard one you asked me for. So
it's not going to pop up in an exam at all.
Well, it's not, but I just want to show you that it's possible. Honestly, I don't think this is a valid molecule. Yeah, but just to get the idea, if this were a valid molecule, and there's no lone pairs on the central atom, the phosphorus and the hydrogens are different. But when we look at their electronegativities, they have the same electronegativity. So even though this atom is different than the others, the length of that vector is the same, and so they would cancel each other out. And so that doesn't happen very often. But I just want to let you know that it could happen so that you don't come back later and say, "You lied to me, Mrs. K." Any other questions? Okay, so the polarity of a molecule is a big deal. It has huge effects on the properties. So polar and nonpolar molecules have very different properties. And one of the things that we observe in everyday life is that oil and water do not mix, right? If you're making soup, the grease rises to the top and it won't mix in. If you're making Italian salad dressing, you shake that bottle up and you set it down and you can just watch it separate, right? The oil separates from the vinegar part. Why? Well, it's because of the polarity and nonpolarity of the water and the oil. So here are our little water molecules. And we just learned that these are polar molecules. And so the oxygen end is a little negative, the hydrogen end is a little positive. Well, these electrical charges are a lot like magnets. And so just like magnets, these water molecules are going to be attracted to each other. Here we have an example of magnetic marbles, which I really need to remember to get some of. I really want to do this in person. Magnetic marbles and glass marbles. And you can imagine from your experience with marbles and magnets what's going to happen here. The magnetic marbles are going to clump together, aren't they? they're going to stick to each other. And the glass marbles are just like whatever. They're just loose, right? If the glass marbles get in the middle of the magnetic marbles, they're going to get just pushed out, right? And that's what happens with the oil molecules in the water. The water molecules stick to each other. They're very attracted by those partial negative and positive charges. They exclude the oil. They push it out. The reason it floats is because it's less dense. But it's excluded because the oil is not polar. It doesn't have these charges, and the water is. Any questions? So here's chemistry in real life. How does soap work? Did you ever think about that?
There's a magic school bus episode.
Oh, you know, the Magic School Bus is so awesome. In fact, I would encourage you to find episodes and watch because so many of them pertain to chemistry. There's an excellent one on electricity, too. So soap. We know that if you get grease on our fingers, like you had toast and you got butter on your fingers, or you greased a pan to make a cake and you've got Crisco on your fingers, you can't just rinse that off with water, right? If you're sticky from the Halloween candy that you ate last night, you can rinse the soap, the sugar off with water, but oil grease doesn't do that. Because the grease is nonpolar and the water is polar and they don't mix together very well. So what soap does is it kind of acts as an intermediate or a go-between. So here we have an illustration of a soap molecule. At one end is a polar head. So here we have oxygens up here, and those are very electronegative. And then over here, the rest of the molecule is carbon hydrogens, and that's going to be very nonpolar. So this nonpolar end is fine mixing in with the grease because the grease or the oil is nonpolar. This polar end likes the water, and so it'll mix in with the water really well. And so what'll happen, let me draw you an ugly picture. So here we have our glob of grease, right? And what happens is the soap molecules will have their tails in the grease, and then they've got their little polar heads on the outside. So you end up with this globule that has these polar heads on the outside, and the water's like, oh, hey, there's a polar thing. Yeah, come be with us, right? And it can get in among the water molecules, and then you've got the water washing away the grease. And that's how soap works. Any questions? Of course, there's lots and lots of different kinds of soap, and they have different qualities and stuff.